So, have you ever wondered what's really going on inside an AI's head? I mean, we see these incredible things they can do, but how they actually get there, it's often a complete mystery, a total black box. Well, today, we're going to pry that box open a little bit. We're going to look at a really clever tool that lets us peek inside and ask a very important question.
And this is the big one, isn't it? Think about it. You could have two different AI models, and both of them can look at a photo and correctly say, that's a cat. But does that mean they saw the cat in the same way? Did one model focus on the pointy ears and whiskers, while the other recognized the overall shape? Are their internal processes basically the same, or are they completely different? How would we even know?
And that's really the heart of it. Just looking at the final answer is kind of like judging two students only by their final test score, without having any idea how they actually studied. To build AI that's smarter, safer, and even more efficient, we've got to find a way to pop the hood and compare their internal logic. Okay, so here's our game plan. We'll kick things off with that core problem. Then use a really simple analogy, a tale of two maps, to make sense of it all. Then we'll introduce the tool for the job, see it in action, check out how it stacks up against the competition, and wrap up with the big takeaway. So let's just zero in on this problem one more time. You can have two AI models that, from the outside, look identical. They get the same answers, they perform the same. But on the inside, their wiring, their internal mechanics could be completely different. And that makes it super hard to know if a model has really learned a concept or if it just found some weird, fragile shortcut to get the right answer.
To really wrap our heads around this, let's actually forget about AI for a minute. We're going to talk about something way more familiar, maps. Trust me, this little analogy is going to make this whole complex idea just click into place.
Okay, picture two maps of a big city. Let's say New York. The first one is for tourists. It's got all the big landmarks highlighted, the Statue of Liberty, Central Park, you get the idea. The second map is for a local. It doesn't care about landmarks, it shows subway lines, bus routes, and all the little shortcuts. Now on the surface, these two maps look totally different, right? But, and this is the key, they both represent the exact same underlying structure of the city. The relationship between one neighborhood and another is the same on both maps, even if they look different. That is the idea we need to hold on to. So let's connect that back to AI. That internal map that an AI builds for itself, that's what we call its neural representation. It's how the model organizes all the data it sees to make sense of everything. And what we really want is a way to compare the structure of these internal maps, not just how they look at a glance. And that brings us to the hero of the hour, the tool that actually lets us compare these hidden maps. It's called Centered Kernel Alignment, or for those of us who like to keep it short, CKA. So what is CKA, really? Well, at its core, it's a clever bit of math that does exactly what we were just talking about. It takes two of these neural representations, our two different maps, and it spits out a score based on their deep, underlying structure. It ignores all the surface-level noise and just asks, are the fundamental relationships the same? And how it works is actually pretty elegant. First, you get a snapshot of what's going on inside two AIs while they're looking at the same stuff. Then, for each AI, you create what you can think of as a relationship fingerprint. You're not just mapping the activity, you're mapping how every point of activity relates to every other point. Then, step 3. CKEA does the math to compare these two fingerprints. And finally, you get a single, simple score telling you how similar they are. And that score is super intuitive. A score that's really close to 1, like 0.95, tells you that, whoa, these two AI models are thinking in a very, very similar way. Their internal maps are structured alike. But a score down near 0, that means their internal worlds are totally different. It's as simple as that. Okay, so this is a cool tool for researchers, but where does it actually, do anything? Let's check out two really amazing applications where CKA is already changing how we build AI. First up is a technique called knowledge distillation. The idea here is pretty straightforward. You've got a massive, super powerful teacher model, and you want to train a smaller, leaner student model to be just as good. It's all about passing knowledge down from the master to the apprentice. This is where CKA plays the role of the perfect exam proctor. Instead of just making sure the student model gets the right answers, CKA checks if the student's internal thought process is starting to look like the teacher's. You can actually use the CKA score to guide the student's training, making sure it doesn't just learn to cheat the test, but that it's truly learning how to think like its teacher. All right, second big use case, a very popular type of model called a mixture of experts, or MOE. Just think of it like a team of specialists. When a new problem comes in, the system routes it to the expert that's best suited for that specific job.
But there's a risk. What happens if all the experts get lazy and just learn to do the exact same thing? That's a problem we call expert collapse.
Well, CKA steps in here as the team manager. While the model is training, we can use CKA to constantly compare the internal maps of all the experts on the team. If the score between two experts starts getting too high, we know they're becoming clones of each other. CKA helps us make sure that every expert stays a specialist with their own unique approach, which makes the whole team way more powerful. It's like quality control for AI minds.
Now, you might be thinking, okay, but surely there are other ways to compare these things, right? And yeah, there are. But CRAKA has a really important advantage that makes it stand out from the simpler methods.
And this is the absolute best way to think about it. The simple methods are basically just asking if two maps are pointing in the same direction. But CKA asks a much deeper question. Is the entire city layout the same? So a basic method might get completely thrown off if you just rotate one of the maps. But CKA is smart enough to see that it's still the same city.
Let's put this head-to-head with a really common alternative, something called cosine similarity. As you can see here, it's pretty limited. It's like asking if two landmarks are in the same general direction from where you're standing. It's quick, but it misses the big picture. CKA, on the other hand, compares the whole relational structure. And that robustness is absolutely critical, because an AI's internal map can be flipped or rotated in all sorts of ways without actually changing what it's learned. CKA sees right through that, which gives us a much more meaningful comparison.
So let's pull all of this together. Why does having a tool like CKA to peek inside this AI black box actually matter so much?
If you take anything away from this, let it be these key points. First, CKA is all about comparing the internal structure, not just the final answers. Always remember those two city maps. Second, this isn't just theory. It has real, practical uses for building better AI, whether that's through knowledge distillation or managing teams of experts. And finally, it really is one of our best tools for turning that AI black box into something a little less mysterious. Tools like CKA give us this incredible new lens to see how an AI thinks, to actually map out its internal logic. But as we get better and better at decoding the how, we're left with an even bigger question, the one you see right here. As these systems get woven into every part of our lives, what part of their artificial minds should we even be trying to understand next? Where do we go from here? Thanks for joining me.